In the previous video, we looked at the sum of a geometric series, and now we're going to look at the sum of an infinite geometric series. To start off with, let's find the sum of the first 10 terms of this geometric series, 1 plus a half plus a quarter, etc. So we know from previously that the sum of a geometric series is equal to the first term times the ratio to the power of the number of terms minus 1, all over the ratio minus 1. And in this case, the first term is 1. We're asked to find the sum of 10 terms, and the ratio is a half. So if we plug that in, the sum of the first 10 terms is equal to 1 times a half to the power of 10 minus 1 over a half minus 1. Simplifying, 2 to the power of 10 is 1024, so we get 1 over 1024 minus 1. To give a common denominator, let's make that 1024 over 1024. And in the denominator, we get negative a half. That's going to be equal to negative 1023 over 1024. And to divide by the fraction, we flip and multiply. So we multiply by negative 2 over 1. And that's going to be equal to, canceling the negatives, canceling 2 out of the numerator and denominator, 1023 over 512, which is almost, but not quite, 2. And that raises an interesting question. It looks like we're going to be adding smaller and smaller numbers every time, because each time the new number is half the previous number that we're adding. So the question is, can we ever get past 2? And it turns out that we can't. If you imagine the initial 1 geometrically as being this rectangle, then the next number that we're adding is a half, so an area half that size. You can imagine that like this. This rectangle is supposed to have half the area of that one. Then the next number we would add would be a quarter of this area. If we put that here, and then add an eighth after that, you can see that we're adding smaller and smaller numbers each time, and you can imagine that the whole thing will eventually fill out this space here, giving us an area of twice what we started with. So it turns out that if you add smaller and smaller numbers each time, because we're going through this geometric series where each number is half the previous one, the final answer will converge on 2. And that can seem very strange because we're adding an infinite number of numbers and getting a finite answer, but it's because each number that we're adding is successively smaller than the one before it. So when a geometric series has a common ratio between 0 and positive 1 or 0 and negative 1, in other words, where the common ratio r is between negative 1 and positive 1, then each successive term we're going to need to add gets smaller, and so the total sum will converge upon, that's the mathematical terminology we use, a finite value. Again, we're adding an infinite number of infinitely small fractions and getting a finite answer. The formula for the sum of an infinite geometric series, in other words, the sum of a series going on to infinity, is sum to infinity is equal to the first term divided by 1 minus the common ratio. So it's actually a simpler formula than we saw previously for a finite number of terms of a geometric series. If we go back to the question that we just looked at, the first term was 1, the common ratio was a half. So if we've plugged that in here, we can see that the sum to infinity would be equal to the first term 1 divided by 1 minus the common ratio. That gives us 1 divided by 1 half, and flipping the denominator and multiplying, we get the 2 that it looked like we were going to get from the previous question. Now you may be wondering, where does this formula come from? Let's go back to the formula for the sum of any number of terms of a geometric series, which we saw in the previous video was this. If we take the top and bottom and think of what's going to happen when the ratio is a fraction between 0 and 1 or 0 and negative 1, this term on the top and this term on the bottom are always going to be smaller than the 1. That means that this whole expression here and this expression here are going to be negative. To simplify things, let's factor a negative out of the top and bottom. If we factor a negative out of this, both signs will change, the sign on r to the power of n and the sign on the negative 1. So we'll get this in the numerator, 1 minus r to the power of n. And in the denominator, if we factor out a negative, again the signs will change, and we'll get negative out front, brackets 1 minus r. Now we can cancel those negatives. And we have a times 1 minus r to the power of n over 1 minus r. Now let's imagine what's going to happen as this n goes towards infinity as that gets very, very big. Remember that in the case that we're looking at here, where r is between 0 and positive 1 or 0 and negative 1, we've got a fraction between 0 and 1 or between 0 and negative 1 to a very large number. That's going to make it smaller and smaller. Imagine, for example, that you have a half to the power of 10, like we did previously, or half to the power of 1,000. This whole thing here is going to go towards 0. That means we're going to have a times 1 minus 0 in the numerator. And overall, then, that's going to simplify to, as n gets towards infinity and r to the n gets towards 0, the whole thing goes to a over 1 minus r. And that's where this formula comes from, how it's derived from the formula we saw previously for the sum of a finite number of terms of a geometric series. Now that we know the formula, let's practice using it. So we could be asked questions like this. Find the sum of this infinite geometric series. And we know right away that the first term is 3, and that the common ratio is a third. And we're asked to find the sum of the infinite geometric series. So we use this formula. The sum to infinity is equal to a over 1 minus r. And then we just plug in. So 3 over 1 minus 1/3 becomes 3 over 2/3. And then to divide by that 2/3 fraction, we flip and multiply. So we get 3 times 3 over 2. And we find that the whole series will converge on a value of 9/2. Here's another example. Use an infinite series to write this as a fraction. So 0.7 repeat. Recall that means 0.7777 going on forever. There's no last digit. It keeps on going with sevens forever. Well, we could break this up because of the pattern and think of it as 0.7 plus, that takes care of that 7, plus 0.07, that takes care of the second 7, plus 0.007, taking care of the third. And we could just keep repeating that infinitely. And this line will express the same thing as the line above. Now we can express each of these as a fraction. The first one is 7/10. The second one is 7/100. The third one is 7/1000. And this is, again, going to go on forever. And now we have a series, an infinite geometric series of fractions. The first term here is 7/10. And if you look to get the next successive term each time, we're multiplying by a common ratio of 1/10. So we have an infinite geometric series with a of 7/10 and r at 1/10, and we can plug it into our formula, a over 1 minus r, and we get 7/10 over 1 minus 1/10, which is 7/10 divided by, this is 10/10 minus 1/10 is 9/10. Again, flipping and multiplying, we get 7/10 times 10 over 9, which is 7/9. So 7/9 is the same as 0.7 repeat. And that's the sum of an infinite geometric series.